At the smallest scales of reality, the universe behaves with extraordinary regularity. Particles appear and interact. Energy shifts between forms. Light moves, scatters, and settles into patterns that can be predicted with remarkable precision. Even uncertainty follows rules, unfolding within carefully measured limits. From these tiny interactions, much of the visible world emerges. Atoms form stable structures. Chemistry unfolds reliably. The properties of materials, the glow of distant stars, and the quiet workings of modern technology all trace back to the same underlying framework. A theory so successful that it seems to explain almost everything the universe chooses to do. And yet, threaded through this success, there is an exception. Gravity is everywhere. It shapes falling rain, rolling tides, and the slow motion of planets through space. It gathers stars into galaxies and bends the paths of light itself. It acts continuously and smoothly, influencing matter across distances so vast they strain intuition. If you enjoy these quiet journeys through deep questions and the edges of what is known, you're very welcome to subscribe and join the Sleepy Scientist. And if you feel like it, sharing where in the world you're listening from tonight can be a gentle reminder of how far these ideas travel. When physicists try to describe gravity using the same quantum ideas that work so well elsewhere, something subtle begins to unravel. The calculations no longer settle into meaningful answers. Predictions lose their physical grounding. The mathematical language that describes particles and energy with such confidence stops cooperating. This is not a small flaw or an unfinished detail. It is a deep mismatch between two ways of describing reality, one built on probabilities and discrete events, the other built on smooth structure and geometry. Both descriptions are extraordinarily successful. Both are supported by decades of observation, and yet, when brought together, they refuse to fully agree. What remains is a gap at the heart of modern physics, not an empty space, but a place where understanding becomes tentative, where certainty softens, and where one of the most familiar forces in existence quietly resists explanation. Tonight's journey moves through that gap, not to force an answer, but to explore why it exists, what it reveals about the universe, and how much can still be learned from what remains unresolved. Settle in, let the questions stay open, and allow the universe to unfold slowly. Modern physics did not grow from a single idea, but from two very different ways of looking at reality. On one side, there is a framework designed to describe the smallest scales imaginable, a world where matter is not solid and continuous, but broken into tiny pieces that behave in surprising ways. At this scale, particles do not follow neat paths. They spread out, interfere with themselves, and only settle into definite outcomes when measured. Cause and effect still exist, but they are wrapped in probability rather than certainty. This way of thinking emerged in the early 20th century, when experiments began to reveal that atoms were not miniature versions of everyday objects. Electrons did not orbit neatly like planets. Light did not always behave like a smooth wave. Energy arrived in discrete amounts, never in between. The universe, it seemed, had a grainy texture beneath its smooth surface. Quantum physics was built to describe this strange territory. It does not ask where a particle is in the usual sense. Instead, it describes where a particle might be and how likely each possibility is. The predictions it makes are not vague or hand-waving. They are astonishingly precise. So precise that the same ideas now underpin lasers, medical scanners, computer chips, and the clocks that keep satellites aligned with Earth. Despite its reputation for weirdness, quantum physics is one of the most successful theories ever constructed. Its predictions have been tested repeatedly across countless experiments, and they continue to hold. When applied to atoms, molecules, and fundamental particles, it works with quiet confidence. Nothing about it feels unfinished in its proper domain. On the other side of modern physics, it's a very different framework, one built not for the tiny, but for the immense. Gravity, as it is currently understood, is not treated as a force passing between objects in the usual sense. Instead, it is described as the shape of space and time themselves. Massive objects do not pull on one another directly. They alter the geometry around them, and other objects simply follow the paths laid out by that geometry. This picture comes from a theory developed in the early 20th century as well, but it speaks a very different language. Where quantum physics deals in probabilities and discrete events, gravity is smooth and continuous. Space curves gently. Time flows at different rates depending on motion and mass. Planets trace predictable paths. Stars orbit calmly within galaxies. On the larger scales, gravity creates structure rather than chaos. This theory has been tested in its own way, and with equal success. It correctly predicts how light bends near massive objects. It explains the slow drift of planetary orbits. It accounts for the behavior of clocks placed at different heights above Earth. It even describes the expansion of the universe itself, a subtle stretching of space that becomes visible only across enormous distances. Just like quantum physics, this theory works extraordinarily well where it is meant to be used. When dealing with stars, planets, black holes, and the large-scale structure of the cosmos, its predictions align closely with observation. There is no obvious sign that it is broken or incomplete within its proper range. And so modern physics rests on two pillars, each sturdy, each reliable, each tested to remarkable precision. The oddity is not that these theories exist. It is that they do not speak to one another. Quantum physics assumes a background stage on which particles move and interact. Space and time are present, stable, and quietly taken for granted. They provide the setting, but they are not part of the drama. The rules describe what happens on that stage, not how the stage itself behaves. The theory of gravity does the opposite. Space and time are not a passive backdrop. They are active, dynamic, and responsive. They stretch, curve, and evolve. The stage is inseparable from the story being told. Individually, each framework makes sense. Together they describe reality using assumptions that do not naturally align. It is a little like having two maps of the same landscape, both accurate, both detailed, but drawn using different coordinate systems that refuse to overlap. One map works perfectly for navigating city streets. The other is ideal for charting the movement of continents. Each is internally consistent, each is useful, and yet placing one on top of the other produces confusion rather than clarity. What makes this especially strange is that both frameworks claim to describe the same universe. The same particles governed by quantum rules also possess mass and energy, which should influence space and time. The same space and time shaped by gravity should, in principle, affect quantum behavior. There is no clean boundary in nature where one theory politely steps aside and lets the other take over. In practice, physicists cope by using each theory where it works best. Quantum physics is used for the small. Gravity is used for the large. Most of the time, this separation works beautifully. Atoms do not noticeably curve space. Planets do not display quantum fuzziness. The universe allows this division to persist without obvious contradiction. But the division itself is peculiar. Reality does not come with labels announcing when one set of rules applies and another does not. There is only one universe, unfolding across all scales at once. That it requires two incompatible descriptions to be understood feels less like a design feature and more like a clue that something deeper is missing. This is not a case of physicists being careless or stubborn. The mismatch has been recognized for decades. Immense effort has gone into trying to reconcile the two views, to find a deeper framework that contains them both as approximations. The difficulty is not a lack of creativity or intelligence. It is that the assumptions built into each theory run in different directions. Quantum physics is comfortable with uncertainty, with outcomes that can only be described statistically. Gravity is deterministic, describing smooth evolution from one moment to the next. Quantum physics treats interactions as exchanges between entities. Gravity treats interaction as geometry itself. One counts possibilities, the other shapes paths. And yet, both are clearly telling the truth about the universe, just in different dialects. The strangeness lies not in their success, but in their separation. The universe appears unified, seamless, and continuous. It does not visibly fracture into quantum regions and gravitational regions, and still, the best descriptions available insist on being used separately, like two lenses that refuse to focus at the same time. Rather than feeling like a failure, this tension hints at depth. It suggests that the universe may be richer than any single framework can capture on its own. That understanding sometimes advances not by fixing what is broken, but by noticing where perfectly good ideas no longer fit together as neatly as expected. For now, physics lives comfortably with this duality. Two theories, one universe. A situation that works well enough to describe almost everything, while quietly reminding us that almost everything is not quite the same as everything. Quantum physics is often introduced as something strange, counterintuitive, even unsettling. But before it became associated with uncertainty and paradox, it earned its place by explaining things that nothing else could. At its heart, quantum physics exists to describe how nature behaves at very small scales. Scales far smaller than dust, cells, or even molecules. Scales where matter no longer behaves like solid objects moving through space, but instead reveals a more delicate and intricate structure. Atoms were one of the first clues that something new was needed. Early models imagined atoms as tiny solar systems, with electrons circling a nucleus in neat paths. But experiments quickly showed that this picture did not match reality. Electrons did not behave like miniature planets. They did not occupy just any orbit they pleased. Instead, they settled into specific arrangements, with precise energies and predictable patterns. Quantum physics provided an explanation that worked. It showed why atoms are stable, why electrons do not spiral inward and collapse, and why different elements have distinct chemical properties. Without this understanding, the periodic table would be little more than a list of observations. With it, chemistry becomes orderly and deeply predictable. From atoms, the theory extends naturally to particles. Electrons, protons, and other fundamental components of matter are not treated as tiny billiard balls. They are described through probabilities spread out in space, capable of behaving like waves under the right conditions. This description sounds abstract, but it produces results that match experiments with astonishing accuracy. When physicists calculate how particles should scatter, interact, or decay, quantum predictions line up with what detectors observe to an extraordinary degree. In some cases, the agreement extends to many decimal places. This level of precision is not common in science. It reflects a theory that is not merely approximate, but deeply tuned to how nature actually works. Light is another area where quantum physics quietly excels. Once thought to be a smooth wave moving through space, light was found to behave in ways that waves alone could not explain. It arrived in discrete packets. It knocked electrons free from metal only when it carried enough energy. Its color mattered more than its brightness in certain interactions. Quantum physics unified these observations into a single picture. Light could behave like a wave or like a particle, depending on how it was observed. This was not a failure of logic, but a refinement of it. The theory did not insist on a single metaphor, it followed the evidence instead. This flexible approach proved remarkably powerful. It allowed scientists to predict how light interacts with matter, how it is absorbed and emitted by atoms, and how it can be controlled with exquisite precision. The result is not just deeper understanding, but practical technology woven into daily life. Lasers, for example, rely entirely on quantum principles. They work because electrons in atoms can be nudged into specific energy states, and then coaxed to release light in a controlled, synchronized way. Medical imaging devices depend on quantum behavior within atomic nuclei. Solar panels convert light into electricity, using effects that make sense only through quantum descriptions. Even the device quietly keeping time for navigation systems relies on quantum physics. Atomic clocks measure time by tracking transitions within atoms that occur with extraordinary regularity. Their accuracy is so high that losing or gaining a second would take longer than many human lifetimes. This reliability is not luck. It is direct consequence of quantum rules being both subtle and exact. What makes all of this especially reassuring is how thoroughly quantum physics has been tested. It has survived challenges across decades in laboratories around the world under conditions ranging from extreme cold to immense energy. Each successful prediction reinforces confidence that, at least within its domain, the theory is describing something real. Importantly, quantum physics does not succeed by being vague. While its language involves probabilities, those probabilities are sharply defined. It does not say that anything can happen. It says exactly how likely each outcome is, and those likelihoods match what experiments reveal when repeated many times. At the center of this predictive power lies a mathematical framework that governs how quantum systems change over time. In its most famous form, this relationship is captured by an equation that describes how the wave description of a system evolves. Written out in words, it states that the total energy of a quantum system is equal to a constant multiplied by the rate at which its wave description changes with respect to time. This equation does not tell a story in plain language, but it works. It allows physicists to calculate how atoms behave, how particles move, and how systems respond to external influences. Its success is measured not by how intuitive it feels, but by how consistently it matches reality. Despite its reputation for mystery, quantum physics is deeply conservative in practice. It does not allow wild deviations. It enforces strict rules. Certain values are permitted, others are forbidden, outcomes are constrained. Nature at small scales turns out to be surprisingly disciplined. This discipline is why trust in the theory runs so deep. When quantum physics is applied correctly, it almost never fails. Disagreements between theory and experiment usually signal missing details or overlooked effects, not a breakdown of the framework itself. Over time, physicists have refined and extended the theory, incorporating additional insights while preserving its core structure. The result is a body of knowledge that feels stable, even if its implications can feel strange. It explains why matter has structure, why light behaves the way it does, and why the microscopic world supports the macroscopic one so reliably. There is also a quiet comfort in this success. Quantum physics suggests that beneath the apparent solidity of the world lies a set of rules that are consistent and universal. The same principles apply whether one is examining a single atom in a laboratory or light arriving from a distant star. And yet all of this confidence is carefully scoped. Quantum physics excels when space and time behave as a steady background. It assumes that distances are well defined, that time flows smoothly forward, and that the stage on which particles act remains stable. Within those assumptions, it performs brilliantly. This is not a flaw. Every theory has boundaries. What matters is that those boundaries are understood and respected. For the most part, the universe cooperates. The situations encountered in everyday life, technology, and most experiments fit comfortably within the quantum framework. Because of this, questioning quantum physics can feel almost ungrateful. It has delivered so much, explained so much, and done so with a level of precision that borders on the uncanny. If any theory has earned trust, it is this one, which is why the tension that appears elsewhere feels so unsettling. Before that tension can be explored honestly, it is important to recognize just how well quantum physics does what it was designed to do. It is not a shaky or speculative idea waiting to be replaced. It is a robust, carefully tested description of reality at small scales. Only by appreciating that success does the real puzzle come into focus. Not that quantum physics fails in general, but that something about the universe refuses to fit entirely within its otherwise dependable reach. Gravity is often introduced as a pull, objects fall, planets orbit, apples drop from trees with dependable enthusiasm. This description works well enough for everyday life, and for centuries it served as a useful way to think about how the universe holds itself together. But this picture, familiar as it is, turns out to be a simplification. Gravity is not quite a force reaching across space and tugging on distant objects. It is something quieter, deeper, and far more expansive in character. In the modern understanding, gravity is the way space and time themselves respond to the presence of mass and energy. This description comes from general relativity, Albert Einstein's theory of gravity. In general relativity, mass and energy determine the geometry of space and time, and objects move according to that geometry. What looks like a pulling force is really motion guided by curved space and time. This shift in perspective can feel subtle at first, but it changes everything. Space is no longer an empty stage where events happen. Time is no longer a uniform clock ticking identically everywhere. Together, space and time form a connected structure, flexible and responsive. When mass or energy is present, that structure bends. When it bends, paths that once seemed straight quietly change their course. A planet orbiting a star is not being held in place by an invisible tether. It is following the straightest possible path through a landscape that is gently curved. From the planet's perspective, nothing is pulling at all. Motion feels natural, almost effortless. The curve is built into the space it moves through. This idea can feel abstract, but its consequences are concrete. Light passing near a massive object changes direction. Clocks tick at different rates depending on how deep they sit in a gravitational field. Distances stretch and shrink in subtle ways. These effects are small near Earth, but they are real, measurable, and essential for modern technology to function correctly. What makes gravity feel especially different from quantum effects is its scale. Gravity does not rush. It does not flicker in and out of existence. It accumulates slowly and acts persistently. A single particle has almost no gravitational influence at all. A mountain has more, a planet more still, a star bends space far more noticeably. Entire galaxies leave deep impressions in the structure of the universe. Unlike the interactions described by quantum physics, gravity does not arrive in discrete packets. There is no smallest unit of gravitational influence that can be isolated and counted. Its effects blend smoothly from one point to the next, forming gentle gradients rather than sharp transitions. This smoothness is part of why gravity feels so calm and predictable at large scales. Orbits repeat, structures endure. The large-scale universe evolves slowly, guided by gravity's steady hand over billions of years. Mass and energy both play a role in shaping this behavior. Anything that carries energy contributes, not just solid matter. Light, pressure, motion, and even the energy stored in empty space all influence how space and time curve. Gravity, in this sense, responds to the total content of the universe, not just its visible pieces. This broad sensitivity gives gravity a universal quality. It does not discriminate between types of matter. It does not switch off at long distances. Its influence extends everywhere, growing weaker with separation but never quite disappearing. Because of this, gravity is responsible for the largest structures ever observed. Galaxies form as matter gradually collects. Clusters of galaxies assemble into vast webs. Filaments stretch across cosmic distances, outlining patterns that span hundreds of millions of light years. All of this unfolds slowly, guided by the accumulated curvature created by mass and energy over deep time. There is a certain patience to gravity's work. While quantum effects dominate the frenetic activity of particles, gravity shapes the long story. It governs the rise and fall of stars, the evolution of galaxies, and the overall expansion of the universe itself. This difference in character matters. Gravity does not share the jumpy probabilistic feel of quantum interactions. It does not demand constant updates or recalculations. Once the shape of space and time is set by the distribution of mass and energy, motion follows naturally. At the heart of this description lies a compact statement that captures the relationship between geometry and content. Written out in words, it says that the curvature of space and time is determined by the distribution of mass and energy within the universe. This idea replaces the notion of force with a relationship between structure and substance. Gravity is not something that happens within space and time. It is something that happens to space and time. This distinction explains why gravity feels so different from other interactions. It doesn't operate against a background. It defines the background. Space and time are not fixed containers waiting to be filled. They are participants in the unfolding of reality. Because of this, gravity resists being localized. There is no single point where gravity resides. It is spread throughout space, encoded in how distances and durations relate to one another. Trying to isolate it the way one isolates a particle misses its essential nature. This also explains why gravity remains so gentle in everyday experience. Earth's mass curves space slightly, enough to keep feet on the ground and guide the moon in its orbit, but not enough to produce dramatic distortions. Life unfolds comfortably within this shallow curvature, rarely noticing it at all. Only in extreme environments does gravity reveal its full strength. Near very dense objects, space bends sharply. Time slows noticeably. Paths that once led outward can turn back on themselves. These regions remind us that gravity is not merely a background condition, but an active, dynamic feature of the universe. Yet even in these extremes, gravity remains smooth. There are no abrupt jumps or flickers. The curvature deepens gradually. The transition from gentle influence to overwhelming dominance unfolds continuously. This continuity stands in quiet contrast to the world described by quantum physics. There, change often comes in steps. Values are restricted. Outcomes are probabilistic. The underlying structure is grainy rather than fluid. Gravity, by comparison, feels like a slow tide rather than a spray of droplets. This difference does not make gravity more real or quantum physics less so. It simply highlights that the universe wears different faces depending on how closely it is examined. At small scales, reality is restless and discrete. At large scales, it is smooth and patient. Understanding gravity as the shaping of space and time allows many phenomena to fall into place. It explains why motion follows predictable paths, why clocks disagree when placed in different conditions, and why the universe can expand without expanding into anything. It also makes gravity harder to treat as just another interaction among many. Its reach is universal. Its influence is geometric. Its effects are inseparable from the structure of reality itself. This is what gives gravity its distinctive presence, vast rather than busy, slow rather than sudden, subtle rather than sharp. It is not a force darting between objects, but a quiet rearrangement of the stage on which all objects move, and it is precisely this quality that makes gravity feel so different from the quantum world. Even though both are essential parts of the same universe, gravity does not shout. It curves, it guides, it waits. And in doing so, it shapes everything from the fall of a stone to the architecture of the cosmos, all without ever behaving like the tiny flickering interactions that dominate the smallest scales of reality. Gravity feels different in a way that most people accept without ever stopping to examine it. Objects fall smoothly. Orbits repeat with quiet reliability. The pull of Earth does not flicker or hesitate, and it does not arrive in bursts. It simply persists, shaping motion in a way that feels steady and dependable. From everyday experience alone, gravity appears calm, continuous, and almost timeless, as though it belongs to the background fabric of reality rather than to the events unfolding within it. That smoothness is not imagined. It reflects something real about how gravity behaves. When gravity influences motion, it does so gradually. Acceleration increases evenly. Paths curve gently. Changes unfold without sharp edges or sudden transitions. Whether watching a stone drop or a planet trace its orbit, gravity reveals itself as a steady guide rather than an impulsive push. This quality becomes especially noticeable when placed alongside the behavior described by quantum physics. At very small scales, nature does not behave as a smooth flow. Energy arrives in discrete amounts. Particles occupy specific allowed conditions and never the spaces in between. Outcomes are not fixed in advance, but described by probabilities that only settle into certainty when measured. Systems do not slide gently from one state to another. They transition, they resolve, they step. Quantum physics is designed for this stepped granular world. It expects it. The theory is comfortable with sharp boundaries and precise limits. Certain values are permitted, others are excluded entirely. At those scales, reality appears structured from pieces rather than continua, as though the universe prefers clear distinctions when examined closely enough. Gravity does not share that texture. There is no smallest unit of gravitational influence that can be isolated and counted. One can weaken gravity by increasing distance, but it never vanishes completely. Its influence thins out gradually, spreading smoothly rather than breaking apart. This continuity is not an accident. It reflects gravity's role as something tied to space and time themselves, rather than an interaction taking place within them. When space and time respond to mass and energy, they do so without jumps. Curvature deepens gently. Paths adjust continuously. Motion follows contours that already exist, as though objects are tracing routes laid out by the universe rather than being tugged along invisible threads. Gravity feels calm because the structure it shapes is calm. Space and time do not flicker or stutter. They bend and stretch patiently, responding to what they contain. Another reason gravity feels so different lies in its extraordinary weakness. This can sound counterintuitive, because gravity dominates everyday experience. It keeps people grounded, oceans pooled, and planets bound to their stars. Against this familiar backdrop, describing gravity as weak can feel almost insulting. But when gravity is compared to the other fundamental interactions, the contrast becomes unmistakable. A small magnet can lift a paperclip against the gravitational pull of the entire Earth. Static electricity can cause lightweight objects to leap upward and cling to surfaces. At the scale of individual particles, electromagnetic effects overwhelm gravity so completely that gravity becomes almost irrelevant. Between particles, gravity is so feeble that it can usually be ignored without any noticeable consequence. This imbalance is not subtle, it is enormous. Gravity is weaker than the other interactions by a margin so vast that it resists everyday intuition. The reason gravity still shapes the universe so effectively is not because it is strong, but because it is universal. Every piece of mass contributes. Nothing cancels it out. Over large collections of matter, its gentle influence accumulates steadily until it becomes dominant. This explains why gravity governs planets, stars, and galaxies, but plays almost no role inside atoms. Quantum physics dominates the microscopic world because the forces acting between particles, they are vastly stronger than gravity. Gravity is present, but drowned out, like a whisper beneath a crowded room. Only when matter gathers in enormous quantities does gravity's influence rise above the noise. Because of this, gravity behaves like a background presence rather than a sharp event. It shapes motion globally rather than locally. It influences trajectories without announcing itself in sudden bursts. Quantum effects, by contrast, often appear vividly in isolation. A single atom can display unmistakable quantum behavior. A single particle can interfere with itself. A single interaction can produce outcomes that feel surprising and counterintuitive. Gravity does not reveal itself that way. It requires scale. It builds influence slowly, adding countless tiny contributions together until they become impossible to ignore. Its smoothness is not a sign of simplicity, but a consequence of averaging. The more mass involved, the more continuous gravity appears. There is also a difference in how uncertainty enters the picture. Quantum physics treats uncertainty as fundamental. Outcomes are not merely unknown, they are genuinely probabilistic. The universe, at small scales, does not always choose a single path until observation forces a resolution. This uncertainty is not a flaw or a limitation. It is built into the structure of the theory itself. Gravity, as it is currently understood, does not contain this kind of uncertainty. Given the distribution of mass and energy, the curvature of space and time follows deterministically. Motion proceeds along predictable paths. Differences in outcome arise from complexity, not chance. Gravity does not gamble, it unfolds. These contrasts make the mismatch between gravity and quantum physics feel intuitive rather than technical. Quantum physics resembles a world made of grains, each capable of behaving independently within strict rules. Gravity resembles the shape of the landscape itself, guiding motion without regard for individual grains. One describes the pieces, the other describes the shape they collectively create. Most of the time, the universe keeps these two domains neatly separated. Gravity is too weak to disturb quantum systems. Quantum effects average out long before gravity becomes noticeable. Nature allows this division to persist without obvious conflict, and so the tension remains hidden beneath the surface. Only in rare environments does that separation begin to fail. When matter is compressed to extreme densities, gravity strengthens dramatically. When distances shrink toward the smallest meaningful scales, quantum effects become unavoidable. In those situations, smooth curvature and granular behavior are forced into direct contact, and neither framework can comfortably ignore the other. What makes this unsettling is not simply that calculations become difficult, it is that intuitions collide. One framework assumes continuity, the other insists on discreteness. One flows, the other steps. Both describe reality accurately within their own domains, yet they rely on fundamentally different instincts about how the universe behaves. Gravity feels different because it is different. Not weaker in importance, but quieter in expression. less abrupt, more patient. It does not announce itself in flashes or jumps. It curves, accumulates, and waits, shaping the universe so gently that its deepest questions can remain hidden in plain sight. Scale matters in physics because the universe behaves very differently depending on how closely it is examined. What feels solid and predictable at one level can become strange and uncertain at another. Laws that describe motion perfectly well for planets begin to fail for particles. Rules that govern atoms say almost nothing about galaxies. Reality does not change its nature from moment to moment, but the way it presents itself shifts dramatically with size, distance, and mass. This sensitivity to scale is not a flaw in physics. It is a feature of the universe itself. Nature does not offer a single set of behaviors that applies equally everywhere. Instead, different patterns emerge depending on whether attention is focused on the very small, the very large, or the spaces in between. Physics, as a result, has learned to speak in different dialects, each tuned to a particular range of scales. At the smallest scales, quantum effects dominate completely. Here, particles do not behave like tiny versions of everyday objects. They spread out. They interfere with themselves. They occupy allowed conditions rather than arbitrary ones. Interactions happen in discrete steps, and outcomes are described by probabilities rather than certainties. At this level, gravity is so weak that it barely enters the conversation at all. Inside atoms, the forces shaping behavior are overwhelmingly quantum in nature. Electrons respond to electromagnetic influences that are unimaginably stronger than gravity. The structure of matter, the stability of atoms, and the rules of chemistry all arise from quantum behavior. Gravity is present, but its influence is so faint that it can be ignored without consequence. The quantum world does not need gravity to explain its everyday workings. At the opposite extreme, gravity takes over. When dealing with planets, stars, galaxies, and the large-scale structure of the universe, quantum effects fade into the background. Individual particles no longer matter. Their collective mass does. Gravity accumulates. It shapes orbits, sculpts galaxies, and governs the expansion of space itself. At these scales, the smooth curvature of space and time dominates behavior, and quantum fluctuations average out until they become negligible. Between these extremes lies a wide middle ground where everyday life unfolds. Objects are large enough for gravity to be noticeable, yet small enough for quantum effects to remain hidden. A falling cup obeys classical motion. A thrown ball follows a predictable arc. Buildings remain standing. Materials behave reliably. The world feels stable and intuitive because the scales involved allow gravity and quantum effects to stay politely out of each other's way. This separation by scale is remarkably effective. Quantum physics handles the microscopic. Gravity handles the cosmic. For most practical purposes, the boundary between them is clean. Each theory can be applied where it works best, and the results are accurate enough to build technology, navigate space, and describe the history of the universe. The difficulty arises only in situations where scale forces the two to meet. Such situations are exceedingly rare. They require enormous amounts of mass compressed into extraordinarily small regions, or distances shrunk to extremes far beyond everyday experience. In these environments, gravity becomes strong enough that its effects can no longer be ignored at small scales, while quantum behavior remains unavoidable because of the size involved. Black holes are one such example. Near their cores, matter is squeezed to densities so high that gravity becomes intense on scales where quantum effects should matter. The early universe provides another. At its beginning, the entire observable cosmos was compressed into a region small enough that quantum behavior and gravitational curvature were both essential to the story. Outside of these exceptional cases, nature keeps the two regimes separate. Atoms do not curve space in any noticeable way. Galaxies do not behave like quantum objects. The universe offers very few places where both descriptions are required at once. This rarity helps explain why the problem took so long to fully reveal itself. For decades, physicists could work comfortably within one framework or the other. Quantum theory flourished in laboratories. Gravity guided astronomy and cosmology. Each theory solved the problems it was designed to address, and neither demanded immediate reconciliation with the other. There was no everyday experiment screaming that something fundamental was wrong. No household object behaved in a way that required both quantum rules and strong gravity to be explained. The mismatch remained hidden in extreme corners of the universe that were difficult, and sometimes impossible to probe directly. In this sense, scale acted as a kind of natural buffer. It allowed physics to progress rapidly without forcing a premature confrontation between incompatible ideas. The separation made it possible to build confidence in both theories independently, to test them thoroughly, and to trust their predictions within their proper domains. There is also a psychological aspect to this delay. Human intuition is shaped by the middle scales of experience. People live in a world where gravity is gentle and quantum effects are invisible. It feels natural to think in terms of smooth motion and solid objects. The idea that reality behaves very differently at other scales can be accepted intellectually, but it does not demand constant attention. As a result, the places where the theories truly clash felt remote. Black holes were distant curiosities. The earliest moments of the universe were inaccessible. These were not problems that interfered with building machines, predicting chemical reactions, or sending spacecraft to other planets. They could be set aside without practical consequence. Only as observations improved did the tension become harder to ignore. Better telescopes revealed environments where gravity grows extreme. More precise measurements hinted at limits in existing descriptions. Questions that once felt abstract began to press closer to observation. Even so, the separation by scale remains one of the universe's most effective disguises. It hides the disagreement between quantum physics and gravity behind a vast range of conditions where each theory works beautifully on its own. Most of the time, the universe behaves as though it has chosen sides, allowing one framework to dominate while the other remains silent. This makes the problem of unifying them feel oddly detached from everyday reality. It is not a crack that spreads visibly across the surface of physics. It is a fault line buried deep beneath layers of successful explanation. Understanding the role of scale helps make this less mysterious. The theories do not fail because they are careless or incomplete. They fail to meet because the universe rarely asks them to operate together. Nature itself enforces the separation, keeping quantum effects small where gravity is strong, and gravity weak where quantum effects dominate. That separation has been a gift as much as a challenge. It allowed physics to grow, mature and succeed across an enormous range of phenomena. It also delayed the moment when the deeper tension had to be faced. Now, as attention turns increasingly toward the edges of what can be observed and understood, scale no longer hides the problem as effectively. The rare places where both descriptions should matter begin to feel less like exceptions and more like clues. They suggest that the universe has been quietly accommodating two ways of speaking about reality, each suited to a different range of scales, while waiting for a deeper language that can describe them both at once. Trouble begins not when either theory is used on its own, but when they are asked to speak to each other. Each framework is internally consistent, carefully tested, and remarkably successful within its own domain. The difficulty arises when physicists try to apply both sets of rules to the same situation and discover that they do not naturally align. At first, the attempt seems straightforward. Quantum physics has a well-established way of describing interactions. gravity has a well-established way of shaping space and time. In principle, one might expect that gravity could simply be treated as another influence within the quantum picture, or that quantum effects could be layered gently onto the curved geometry described by gravity. In practice, this expectation quickly dissolves. When physicists try to treat gravity as a quantum interaction, the calculations begin to behave strangely. Quantities that should remain finite instead grow without bound. Small corrections balloon into enormous contributions. Predictions lose their connection to anything measurable. The mathematics does not merely become difficult, it stops making physical sense. This breakdown is not subtle. It is not a matter of missing a term or choosing the wrong approximation. The structure of the calculation itself begins to unravel. Instead of producing sensible answers, it produces infinities that cannot be removed without destroying the logic of the theory. To understand why this happens, it helps to remember what each framework assumes. Quantum physics is built on the idea that interactions take place against a fixed background of space and time. Distances and durations are assumed to be well defined. The stage is set and particles act upon it. Gravity refuses this arrangement. In the gravitational description, space and time are not fixed. They respond dynamically to mass and energy. The stage itself moves, bends, and evolves. Trying to quantize gravity is therefore not like quantizing a force acting on a stage. It is like trying to quantize the stage itself. When these assumptions collide, calculations lose their footing. Quantum methods expect a stable background that gravity does not provide. Gravitational descriptions expect smooth geometry that quantum fluctuations disrupt. Each framework pulls the mathematical structure in a different direction. Physicists have not been idle in the face of this problem. For decades, they have tried clever rearrangements, alternative formulations, and increasingly sophisticated tools. They have explored new ways of organizing calculations and new perspectives on what the fundamental ingredients of reality might be. And yet the same pattern keeps appearing. Whenever gravity is pushed fully into the quantum framework using familiar methods, the theory becomes unstable. The numbers refuse to settle. The predictions refuse to behave. The framework ceases to be predictive. This is not because gravity is especially messy or because quantum physics is poorly constructed. Both are elegant in their own way. The difficulty lies in how deeply their assumptions are woven into their structures. Each theory encodes a different idea about what space and time are, and those ideas cannot simply be layered on top of one another. There is a quiet kind of frustration in this realization. It is not the frustration of repeated failure, but the frustration of clarity. The problem is not hiding. It reveals itself quickly and consistently, as though the universe is politely but firmly declining the invitation to merge these descriptions without something more fundamental changing. One way to see this is to notice how each theory treats scale. Quantum physics expects that zooming in reveals finer detail. Gravity expects that zooming in reveals stronger curvature. When both expectations are applied at once, the result is not a richer picture, but a clash of interpretations. The same region of reality is being described in two incompatible ways. This clash shows up mathematically as runaway behavior. Calculations that work beautifully for other forces suddenly become uncontrollable. Attempts to correct them lead to more problems rather than fewer. It is as though the usual tools are being applied to a surface that simply does not support them. Importantly, this does not suggest that either theory is wrong. On the contrary, their success elsewhere makes the failure to combine them more striking. If either framework were sloppy or unreliable, the mismatch could be dismissed as a technical inconvenience. But both are among the most carefully tested ideas in science. The refusal to cooperate therefore feels intentional in a way, not dramatic or defiant, but consistent. Gravity and quantum physics each insist on their own view of reality, and neither is willing to yield without a deeper revision of the underlying picture. This realization has shifted how physicists think about the problem. Rather than treating it as a matter of finding the right calculation, many now see it as a signal that something fundamental is missing. The issue may not be how gravity fits into quantum physics, or how quantum effects fit into gravity, but how both emerge from a deeper framework that has yet to be fully understood. There is a certain humility in this perspective. It accepts that even the most successful ideas can have limits. It acknowledges that progress sometimes requires stepping back, rather than pushing forward with greater force. The difficulty of unifying these theories has also helped clarify their strengths. By watching where they fail to overlap, physicists gain insight into what each one assumes about the universe. The mismatch becomes informative rather than merely obstructive. In this sense, the refusal of the theories to cooperate is not an embarrassment. It is a guide. It points toward the places where intuition needs revision and where new concepts may be required. The frustration that arises here is quiet and intellectual. It does not come from lack of effort or imagination. It comes from repeatedly encountering the same structural barrier, no matter how carefully the problem is approached. The universe appears to be telling a consistent story, even if that story is incomplete. Rather than forcing a resolution, many physicists have learned to listen to that story more closely. The breakdown itself becomes part of the evidence. It suggests that space, time, and matter may be related in ways that neither framework fully captures on its own. When theories refuse to cooperate, it is tempting to see the situation as a dead end. But in physics, such moments often mark the edge of understanding rather than its failure. They indicate that the language being used has reached its limits. Gravity and quantum physics do not argue loudly. They simply talk past each other. And in that quiet disagreement lies one of the deepest clues we have about how much remains to be understood about the structure of reality itself. The search for a deeper understanding of gravity did not begin because something was obviously broken. It began because something was quietly unfinished. Once physicists realized that the universe was being described by two powerful but incompatible frameworks, the question was unavoidable. If both descriptions are true, then something more fundamental must sit beneath them. This realization has been guiding research for decades, not as a single project with a clear endpoint, but as a long, patient effort to understand what gravity really is when examined at the smallest meaningful scales. The goal is not to discard what already works, but to discover a framework that explains why those successful ideas exist in the first place. What makes this problem feel foundational is that gravity is not just another interaction among many. It shapes space and time themselves. Any attempt to unify it with quantum physics therefore touches the deepest assumptions about how reality is structured. Questions about gravity quickly become questions about space, time, matter, and even what it means for something to exist at all. Because of this, the search for quantum gravity is not driven by a single experimental anomaly or practical need. It is driven by consistency. Physics aims to tell a coherent story about the universe, one that does not rely on separate rulebooks depending on scale. As long as gravity and quantum physics remain disconnected, that story feels incomplete. This sense of incompleteness has motivated generations of physicists. Some have approached the problem mathematically, exploring how the language of quantum theory might be reshaped to accommodate gravity. Others have started from gravity itself, asking how its geometric description might change when examined closely enough. Still others have questioned assumptions that both theories share, wondering whether space and time themselves might not be fundamental after all. What unites these efforts is not agreement on method, but patience. Progress in this area has been slow and often indirect. There have been promising ideas, partial successes, and occasional false starts. None of this is unusual. Foundational problems rarely yield to quick solutions, especially when they involve rethinking concepts that have worked remarkably well for so long. It is also important to recognize what this search is not. It is not a competition to replace existing theories. Quantum physics and gravity are not rivals fighting for dominance. Each continues to do its job extraordinarily well. The goal is not to declare a winner, but to understand how both fit into a larger picture. In many ways, the effort resembles careful exploration rather than construction. Physicists probe the edges of known theories, looking for hints of deeper structure. They examine where calculations fail, where assumptions clash, and where new ideas might naturally arise. The process is less about bold declarations and more about listening closely to what the mathematics and observations are quietly suggesting. Because the problem is so deep, researchers have learned to be cautious about claims. Grand unifying ideas are tempting, but nature has shown little interest in accommodating shortcuts. Any successful description of quantum gravity must reduce to quantum physics where gravity is weak, and to the current theory of gravity where quantum effects are negligible. It must respect what is already known while extending understanding into unfamiliar territory. This requirement alone imposes a remarkable level of discipline. It ensures that new ideas remain grounded, even when they venture far from familiar intuition. It also explains why progress can feel incremental rather than dramatic. Each step must fit seamlessly into a vast existing structure of knowledge. There is also a cultural aspect to this search. The problem has encouraged collaboration across fields that once felt distant. Particle physicists, cosmologists, mathematicians, and philosophers have found themselves asking overlapping questions. What is space made of? How does time emerge? Are there limits to what can be measured? These are not questions confined to a single discipline. Despite the abstract nature of the work, there is a quiet optimism that runs through it. Not the optimism of expecting a solution tomorrow, but the optimism of believing that the universe is intelligible, that the patterns observed so far are not arbitrary, but part of a deeper order waiting to be uncovered. Gentle humour occasionally surfaces in how physicists talk about the problem. There is an awareness that trying to unify gravity and quantum physics can feel like persuading two stubborn languages to share a grammar. Each speaks fluently on its own, yet resists translation. The task is not to shout louder, but to learn how to listen differently. This long view helps explain why the search has continued even in the absence of direct experimental confirmation. Some of the scales involved are so extreme that building the necessary experiments may take generations, or may never be fully possible. Rather than discouraging inquiry, this limitation has sharpened it. It forces ideas to be internally consistent, mathematically robust, and conceptually clear. The search for quantum gravity is therefore as much about refining understanding as it is about discovery. Even approaches that ultimately turn out to be incomplete can illuminate hidden assumptions or reveal unexpected connections. In this way, progress is not measured solely by answers, but by the quality of the questions that emerge along the way. There is also a sense of continuity with the past. Physics has faced similar moments before, when existing theories worked well within their domains but failed to align. Each time, resolution required a shift in perspective rather than a simple correction. Remembering this history encourages patience. It suggests that confusion is often a prelude to clarity. What makes the current situation distinctive is how successful the existing theories are. Quantum physics and gravity are not rough approximations waiting to be replaced. They are precise, reliable, and deeply trusted. Any unifying framework must therefore be subtle enough to preserve their successes while explaining their differences. This is why the search feels less like chasing a missing piece and more like uncovering a hidden layer. Gravity may not simply be another quantum force waiting to be described. Quantum physics may not simply need a small adjustment to include gravity. Both may be reflections of something more fundamental that has not yet been fully recognized. Seen this way, the problem becomes less frustrating and more intriguing. The refusal of the theories to merge easily suggests that the universe is guarding a deeper secret, one that requires patience, creativity, and humility to approach. Rather than racing toward a conclusion, physicists continue to explore, refine, and question. The search for quantum gravity unfolds slowly, shaped by curiosity rather than urgency. It is driven by a desire to understand, not to conquer. In that sense, the effort mirrors the universe it seeks to describe: vast, intricate, and patient. A reminder that some of the most important questions are not meant to be answered quickly, but to be lived with, explored, and gradually illuminated over time. Studying gravity at quantum scales turns out to be difficult for a reason that is both simple and deeply inconvenient. Gravity is extraordinarily weak, and quantum effects only reveal themselves clearly when systems are extraordinarily small. Bringing those two conditions together requires circumstances that sit far beyond anything normally accessible. In everyday experiments, gravity is easy to observe because masses are large and distances are familiar. Drop an object and it falls. Watch the moon and it orbits. But these effects emerge from the combined influence of enormous numbers of particles acting together. At the level of individual particles, gravity is so faint that it is completely overshadowed by other interactions. Quantum experiments, by contrast, thrive on isolation. They are designed to study tiny systems in carefully controlled conditions, often shielded from outside influence. Particles are trapped, cooled, and observed with exquisite sensitivity. In this environment, quantum behavior becomes visible and measurable. Unfortunately, gravity almost entirely disappears from view. Trying to observe quantum aspects of gravity therefore demands a strange combination. One needs systems that are both extremely small and enormously massive, or situations where space and time themselves are distorted at tiny scales. Nature does provide such environments, but they are not conveniently located in laboratories. Black holes are one example. Near their cores, gravity becomes extraordinarily strong, and the distances involved shrink towards scales where quantum effects should matter. But black holes are distant, hostile, and not inclined to cooperate with measurement. They do not sit patiently in experimental chambers. They reveal themselves only indirectly, through their influence on surrounding matter and light. The very early universe presents another opportunity. In its earliest moments, all the mass and energy of the observable cosmos were compressed into an unimaginably small region. Gravity and quantum effects must both have played essential roles. Yet those moments are long past, and their traces are faint. Observations can hint at what happened, but they cannot recreate the conditions directly. This is where the challenge becomes one of technology rather than imagination. Physicists can describe the kinds of experiments that would be ideal. They can outline what measurements would settle key questions. What they cannot do, at least for now, is build the machines required to carry them out. To probe quantum gravity directly would require energies far beyond what current accelerators can reach, or sensitivities far beyond what current detectors can achieve. The scales involved are so extreme that even the most ambitious experiments fall short by vast margins. This is not a matter of incremental improvement. It is a matter of orders of magnitude. That gap can be frustrating, but it is also revealing. It reminds us that physics does not advance only through clever ideas. It advances through tools, materials, and engineering, all of which develop at their own pace. Imagination can move faster than instrumentation, and in this case it has done exactly that. Importantly, The absence of direct experimental confirmation does not imply that progress has stalled. Physicists have learned a great deal by studying indirect effects, consistency requirements, and theoretical consequences. A proposed idea about quantum gravity must agree with everything already known. It must not contradict well-tested results in quantum physics or gravity. These constraints are powerful, even without new data. There's also value in understanding why experiments are difficult. The very fact that gravity is so weak at small scales explains why quantum effects are so cleanly visible in laboratories. It also explains why gravity dominates the cosmos without interfering with chemistry or biology. The difficulty of measurement is itself a clue about how the universe is organized. Sometimes this challenge is framed as limitation, but it can also be seen as a kind of protection. If gravity behaved differently at quantum scales, everyday matter might be unstable. Atoms could fall apart. Chemistry might not exist. The universe we experience depends on the quiet separation of these effects. This perspective helps soften the frustration. The lack of experimental access is not a sign that something has gone wrong. It is a reflection of how nature has arranged itself. Gravity and quantum effects occupy different ranges of scale so effectively that forcing them together requires extraordinary circumstances. Over time, technology does advance. Detectors become more sensitive. Observations become more precise. Experiments once thought impossible gradually come within reach. Gravitational waves, for example, were predicted long before they were detected. Their eventual observation required patience, ingenuity, and decades of refinement. This history offers a useful reminder. The absence of evidence today does not mean evidence will never arrive. It often means that the question is simply ahead of its tools. Physics has encountered this situation many times before, and each time progress eventually followed, though rarely on a convenient schedule. In the meantime, the search continues through indirect paths. Physicists examine cosmic signals, subtle deviations, and theoretical consistency. They look for places where existing descriptions strain, or where new ideas make distinctive predictions, even if those predictions cannot yet be tested directly. There is a quiet discipline in this approach. Rather than declaring defeat, researchers refine their questions. Rather than forcing premature conclusions, they allow uncertainty to remain. This patience is not resignation. It is a recognition that understanding sometimes requires waiting as much as working. Quantum gravity, if it reveals itself experimentally, is unlikely to do so dramatically. There may be no single experiment that settles everything at once. Instead, evidence may accumulate slowly through small hints that align over time. A pattern, rather than a proclamation. Until then, the lack of direct confirmation should not be mistaken for failure. It is a reflection of the scale of the problem and the ambition of the question. Few areas of science attempt to probe such extreme conditions or such fundamental aspects of reality. In this light, the difficulty of experimentation becomes part of the story rather than an obstacle to it. It highlights how far understanding has already come and how carefully the universe guards its deepest workings. Gravity at quantum scales remains elusive not because it is unreachable in principle, but because it lives at the far edges of what can currently be touched, measured, and tested. And in physics, those edges have a long history of slowly, patiently moving outward. Black holes are places where gravity stops being gentle. The slow curvature that guides planets and stars steepens dramatically, folding space and time inward with relentless focus. Matter falls, light bends, and paths that once led outward curve back toward a region from which there is no easy return. These are not violent places in the everyday sense. They are quiet, dark, and patient. But within that calm exterior, gravity reaches its most extreme expression. A black hole forms when enough mass is compressed into a small enough region that gravity overwhelms every other influence. The result is not an object in the usual sense, but a boundary, a surface beyond which the familiar rules of motion no longer allow escape. From the outside, a black hole can appear deceptively simple, defined only by mass, rotation, and electric charge. Inside, the story becomes far more complicated. What makes black holes especially important for physics is not just their intensity, but their scale. Near the heart of a black hole, gravity becomes strong on distances where quantum effects should matter. Space curves sharply, time slows dramatically. The separation between the smooth world of gravity and the granular world of quantum physics begins to collapse. This is precisely the kind of environment where the universe can no longer keep its two descriptions apart. In most places, gravity is too weak to disturb quantum systems, and quantum effects average out before gravity becomes noticeable. Near a black hole, that balance shifts. The curvature of space and time grows so steep that even the smallest details of matter and energy can no longer ignore it. Quantum behavior should become entangled with gravitational structure in ways that neither theory can fully describe on its own. One of the first hints of this tension came from considering what happens near the edge of a black hole. From far away, the boundary appears calm and uneventful. Matter drifts inward. Light grows dimmer. Time slows. But when quantum effects are taken into account, the picture becomes less straightforward. Quantum physics suggests that empty space is not truly empty. Even in darkness, fluctuations occur. Particles briefly appear and vanish. Near a black hole, these tiny effects can be amplified by gravity, leading to subtle but profound consequences. Energy can leak away. Information may not behave as expected. The clean simplicity of the gravitational description begins to fray. This is where cracks in current understanding become visible. According to the gravitational picture alone, anything that crosses the boundary of a black hole is lost forever, carrying its details with it. According to quantum physics, information is never truly destroyed. These two ideas cannot both be correct in their simplest forms. Somewhere near black holes, one or both descriptions must give way to something deeper. The tension does not announce itself loudly. There are no explosions of contradiction. Instead, there is a quiet mismatch, revealed through careful thought and subtle calculation. Black holes force physicists to confront questions that can be safely ignored elsewhere. What happens to information? How does space behave at the smallest scales? Can time itself be treated as a quantum entity? In this sense, black holes function like natural experiments, set up by the universe rather than by human hands. They explore regimes that cannot be recreated in laboratories, compressing mass and energy into configurations that push known theories to their limits. They are not experiments that can be adjusted or repeated at will, but they are consistent enough to study through their effects on surrounding matter and light. The imagery surrounding black holes often emphasizes violence and destruction, but their deeper role is quieter. They sit at the centers of galaxies, anchoring vast structures. They influence stars and gas over immense distances. They shape their environment slowly, over millions and billions of years. Their extremity is local, their presence enduring. This makes them ideal testing grounds, not because they are dramatic, but because they are persistent. They provide long-lived conditions where gravity remains extreme, allowing subtle effects to accumulate and reveal themselves over time. Observations of matter spiraling inward, of light bending around their edges, and of waves rippling outward from their mergers all carry information about how gravity behaves under stress. Yet even with these observations, black holes remain frustratingly opaque. Their interiors are hidden. Their deepest regions cannot be seen directly. Physics must infer what happens there by stitching together clues from theory and observation, knowing that the picture is incomplete. There is a certain humility built into this process. Black holes do not offer answers freely. They challenge assumptions and reward patience. Each insight gained seems to reveal another layer of uncertainty beneath it. Rather than resolving the conflict between gravity and quantum physics, they sharpen it. This sharpening is valuable. It shows that the problem is not abstract or philosophical. It arises in real, physical objects that exist in the universe. Black holes are not thought experiments. They are astrophysical realities shaping galaxies and influencing cosmic evolution. They also remind us that the universe is capable of constructing environments far beyond human engineering. While laboratories struggle to bring gravity and quantum effects together, black holes do so effortlessly, simply by existing. The difficulty lies not in nature's ability to combine these regimes, but in our ability to describe what happens when it does. In the quiet darkness near a black hole, familiar concepts begin to blur. Space behaves strangely. Time stretches and compresses. The distinction between inside and outside becomes subtle. These are not just curiosities. They are signs that the language used to describe reality is being pushed beyond its comfortable range. Black holes therefore occupy a special place in the search for understanding. They are not merely objects of fascination, but guides. They show where existing theories strain and where new ideas may be needed. They expose cracks not by breaking physics, but by revealing where its seams lie. Seen this way, black holes are less like monsters and more like mirrors. They reflect the limits of current understanding back at those who study them. They ask questions rather than provide answers, and they do so without urgency or drama. They sit quietly in the universe, shaping space and time, waiting. And in their silence, they offer one of the clearest invitations to rethink how gravity and quantum physics might finally learn to speak the same language. To understand why gravity and quantum physics must eventually meet, it helps to look not outward into space, but backward in time. Far beyond galaxies and black holes lies an earlier chapter of the universe's story, one so distant that it can only be approached indirectly. The very beginning, when everything that now exists was once packed into a state unimaginably hot, dense, and small. In the earliest moments of the universe, scale collapses in every direction. Distances shrink, energies rise, time itself behaves differently. The familiar separation between the very large and the very small disappears, not because theories fail, but because the universe itself no longer provides room for them to remain apart. At that time, gravity could not afford to be gentle. With so much mass and energy compressed into such a tiny region, the curvature of space and time must have been extreme. At the same time, the universe was small enough that quantum effects were unavoidable. There was no quiet background, no stable stage. Everything happened at once, everywhere, under conditions that demanded both descriptions simultaneously. This makes the early universe one of the most important testing grounds for understanding reality at its deepest level. Unlike black holes, which are rare and scattered, the early universe was universal. Every region of space passed through that phase. Whatever rules governed those earliest moments helped shape everything that followed. Modern cosmology does a remarkable job of describing the universe after those first instants. It explains how space expanded, how matter cooled, how atoms formed, and how galaxies eventually emerged. Observations of distant light and subtle patterns in cosmic radiation align beautifully with these models. From a fraction of a second onward, the story unfolds with impressive clarity. But when attention is pushed closer to the beginning itself, the picture begins to blur. Current models rely on gravity described in smooth classical terms. They assume space and time behave as continuous structures, even at the earliest times. This assumption works well for much of cosmic history, but as the clock is wound back further, it becomes increasingly strained. Distances approach scales where quantum effects should matter. Energies rise to levels where fluctuations cannot be ignored. At some point, the mathematics stops being trustworthy. Not because it explodes dramatically, but because the assumptions underneath it quietly lose their footing. The equations still exist, but their connection to physical reality becomes uncertain. The description begins to lean on ideas that no longer clearly apply. This does not mean the early universe was chaotic or unknowable in a dramatic sense. It means that the tools currently available are not designed for that regime. They describe what happened after the universe had already settled into a form where gravity and quantum effects could remain mostly separate. Before that settling, something else must have been at work. What exactly happened in those earliest moments remains one of the most delicate questions in science. Not because it is inaccessible, but because it sits at the intersection of two incomplete descriptions. Gravity wants to describe the evolution of space and time as a whole. Quantum physics wants to describe fluctuations, probabilities, and discrete behavior. In the early universe, both demands are unavoidable. This creates a kind of conceptual fog. Models can approach the beginning, but not quite reach it. They can describe how conditions evolved from an early state, but not fully explain what that state was or how it behaved. The closer one looks, the more the language of physics begins to soften. Importantly, this uncertainty is not treated as a catastrophe. It is not seen as a breakdown of understanding, but as a boundary, a horizon beyond which current descriptions lose their sharpness. Just as telescopes have limits beyond which light cannot be gathered, theories have limits beyond which assumptions no longer hold. The early universe is one such limit. There is something quietly humbling about this. The universe, in its infancy, does not reveal itself easily. It leaves behind traces, patterns, and echoes, but not a complete record. The earliest moments are inferred rather than observed, reconstructed rather than remembered. This distance in time adds to the sense of mystery. The early universe is not something that happened somewhere else. It happened here, everywhere. Yet it remains profoundly unfamiliar. The laws that govern everyday experience had not yet settled into their current form. Space and time themselves may have behaved in ways that have no direct analogue today. Speculation inevitably enters this territory, but it is careful and restrained. Physicists explore possibilities rather than certainties. They ask what kinds of behavior could smooth the transition from a quantum-dominated beginning to a gravity-dominated expansion. They examine how small fluctuations might have grown into the large structures seen today. What they avoid is pretending to know more than the evidence allows. This restraint is part of what makes the problem compelling rather than troubling. The early universe is not a failure of explanation. It is a reminder that explanation has a scope. Beyond that scope lies inference, imagination, and patient inquiry. There is also a sense that the early universe holds answers not just about gravity and quantum physics, but about why the universe looks the way it does at all. Why space appears smooth on large scales. Why time flows in a particular direction. Why the constants of nature fall within the ranges they do. These are not questions that can be addressed fully without understanding those first moments. Yet the universe does not rush us toward answers. It allows the mystery to remain gentle. The early universe is not presented as a violent explosion in this context, but as a quiet beginning whose details are softly veiled. A place where familiar concepts blur, not into chaos, but into something subtler. In this way, the early universe mirrors the challenge of unifying gravity and quantum physics itself. Both sit just beyond the reach of current tools. Both reveal their presence through indirect signs rather than direct access. Both suggest that understanding will come not through force, but through refinement. The difficulty is not that gravity and quantum physics contradict each other violently at the beginning of time. It is that they overlap in a way that neither was designed to handle alone. Their assumptions collide gently, producing uncertainty rather than outright failure. This gentleness matters. It keeps the question open rather than overwhelming. It invites careful thought rather than dramatic revision. The early universe does not demand immediate answers. It waits. Seen from this perspective, the beginning of the universe is not a wall but a threshold, a place where existing descriptions fade, making room for something deeper to emerge. Whatever that deeper framework turns out to be, it will need to speak comfortably about both the smooth unfolding of space and the restless behavior of quantum systems. Until then, the earliest moments remain softly unknowable, not lost, not broken, but held at a respectful distance. A reminder that even in a universe described with extraordinary precision, there are still regions where understanding arrives slowly, carried forward by patience rather than certainty. The early universe does not shout its secrets, it whispers them faintly across billions of years, and physics, listening carefully, continues to learn how to hear. For most of modern physics, there is an assumption that sits quietly in the background. Gravity is treated as one of the fundamental forces, alongside others that govern how particles interact. Different in character, certainly, but still part of the same basic category. Something that should, in principle, have a quantum description just like everything else. But as the effort to unify gravity with quantum physics has stretched on, an intriguing question has become harder to avoid. What if gravity is not quite the same kind of thing as the other forces? What if the struggle is not merely technical but conceptual? What if gravity is not waiting to be quantized in the usual way, because it is not a conventional quantum force at all? This idea is controversial for a simple reason. Quantum physics has been astonishingly successful at describing interactions in terms of quantum fields and discrete exchanges. It has explained enormous amounts of nature by treating forces as arising from underlying quantum behavior. In that context, it feels natural to assume gravity should fit into the same pattern. If everything else can be described quantum mechanically, why would gravity be exempt? And yet, gravity has always had an odd status. It does not simply act within space and time, it shapes them. That distinction sounds like wordplay until it is taken seriously. If gravity is the structure of space and time, then treating it like a force travelling through a fixed background may be the wrong starting point. Perhaps gravity is not another actor on the stage. Perhaps it is part of what makes the stage exist in the first place. This possibility is intriguing because it reframes the problem. Instead of asking how gravity can be made to behave like the other forces, it asks whether the other forces are being understood in the right context. Gravity might not be the odd one out. It might be the foundation the others quietly rely on, a deeper layer of organization that does not fit neatly into the same quantum framework. There are reasons physicists take this seriously, even if cautiously. The trouble with combining gravity and quantum physics is persistent and structural. The mismatch does not vanish with clever algebra or improved approximations. Again and again, gravity resists being treated as just another interaction. That resistance could be a sign that something is missing at the level of assumptions. In science, these moments can be fertile. When a problem refuses to yield, it can be an invitation to examine the starting point rather than the method. Physics has advanced in the past by questioning what seemed obvious. Time was once assumed to be universal and absolute. Space was once assumed to be a fixed container. Light was once assumed to require a medium to travel through. Each of these assumptions felt reasonable until evidence and theory gently forced a shift. In that spirit, questioning whether gravity is a quantum force is not an act of rebellion. It is an act of curiosity. It asks whether the universe is given a clue through its refusal to cooperate. One speculative possibility is that gravity might be emergent, meaning it arises from deeper processes rather than existing as a fundamental interaction on its own. This idea appears in different forms across theoretical work, but the intuitive picture is simple. Some phenomena look fundamental when viewed from one scale, yet emerge naturally when viewed from a deeper layer. Temperature, for example, feels like a basic property of a substance, yet it arises from the collective motion of countless particles. There is no temperature in a single molecule. Temperature emerges from the group. In this view, gravity might be more like temperature than like a fundamental force. It could arise from the collective behavior of microscopic ingredients of reality that are not themselves gravitational in the usual sense. Space and time might have underlying building blocks, and gravity might be the large-scale behavior that results when those building blocks interact. This is not a settled idea, and it is not universally accepted. It is difficult to test, and it can be described in ways that range from elegant to highly speculative. But it is intriguing because it would explain why gravity feels smooth and continuous. If gravity is an emergent, averaged effect, then its continuity would be a natural consequence of many small contributions blending together. It could also explain why quantizing gravity directly has been so hard. If gravity is not fundamental, then trying to treat it as a quantum force might be like trying to quantize the concept of temperature. One can study the molecules that give rise to temperature, and those molecules are quantum. But temperature itself is not a fundamental quantum object. It is a macroscopic description. Perhaps gravity belongs in a similar category. Another speculative thread asks whether space and time themselves may not be fundamental. Quantum physics typically assumes a background of space and time in which events occur. Gravity suggests that space and time are dynamic. Unifying the two may require a picture where space and time emerge from something deeper, with quantum behavior woven into that emergence from the start. This is a difficult idea to hold in the mind, because it requires stepping away from familiar intuitions. Space feels like the most basic thing imaginable. Time feels like the steady heartbeat of reality. Suggesting that these might be emergent can feel like suggesting that the floor is optional. Even so, physics has repeatedly found that what feels basic is not always fundamental. Solid surfaces are mostly empty space at the atomic level. Continuous motion becomes discrete energy levels inside atoms. Certainty becomes probability when examined closely enough. In that context, wondering whether space and time emerge is not entirely out of character for the universe. Still, the controversy remains. Many physicists believe gravity must have a direct quantum description, even if it is difficult to formulate. They argue that gravity couples to energy, and quantum systems carry energy, so gravity must in some sense be quantized. They point out that other forces once seemed mysterious until the right framework was found. In their view, gravity is simply the last one waiting for its quantum language. This perspective is reasonable, and it remains the dominant expectation. It also keeps the search focused. If gravity is quantizable, then the goal is to find the correct theory, confirm it experimentally, and fold gravity into the broader quantum picture. But the alternative perspective persists, because it addresses something more philosophical as well as physical. It asks whether the desire to unify comes from nature or from human preference. It asks whether the universe truly demands a single description at all scales, or whether different descriptions emerge naturally at different levels. These questions can sound abstract, but they touch real problems. Black holes, the early universe, the breakdown of calculations. the stubborn refusal of infinities to behave, each of these suggests that existing categories may not be sufficient. The uncertainty here should remain gentle. There is no need to declare gravity non-quantum or to insist that it must be. The honest position is that the universe has not yet made its answer fully visible. What can be said is that gravity behaves unlike the other forces in key ways. It shapes the background rather than acting within it. It appears smooth where quantum behavior is granular. It resists quantization using familiar tools. That resistance might mean gravity is special, or it might mean current understanding is incomplete, or it might mean both. In science, progress often begins when someone asks a question that feels slightly uncomfortable, not because it is dramatic, but because it forces a reassessment of what has been taken for granted. The question of whether gravity is a quantum force is one of those. It does not promise an answer, but it opens a space for new thinking. And in that space, curiosity becomes more important than certainty. Gravity may turn out to be quantum in the end, described in a language that has not yet been found. Or it may turn out to be emergent, a large-scale effect of deeper ingredients. Either way, the process of asking the question is valuable, because it sharpens understanding of what is known and what is assumed. For now, gravity remains slightly apart, familiar, steady, and everywhere, yet still resisting full incorporation into the quantum world. Whether that resistance is a clue about gravity itself, or a clue about the limits of current categories, remains softly open. The universe, as always, is in no hurry to settle the matter. At some point in every deep scientific question, it becomes useful to pause and ask what is actually being sought. When physicists say they want to explain something, what do they mean by that word? Is explanation about prediction, about description, or about something closer to understanding? Science is exceptionally good at prediction. Given the right conditions, it can tell how systems will behave with astonishing accuracy. It can forecast the motion of planets, the behavior of atoms, the bending of light, and the evolution of stars. These predictions are not vague guesses. They are precise, repeatable, and often breathtakingly reliable. But prediction and understanding are not always the same thing. It is possible to predict without feeling that anything has truly been explained. A set of rules can work flawlessly while still leaving the deeper picture feeling incomplete. The rules may describe what happens, but not why it happens in that particular way, or why those rules exist at all. This distinction matters when thinking about gravity and quantum physics. Both theories predict outcomes with remarkable success in their respective domains. Quantum physics predicts the behavior of particles and light. Gravity predicts the motion of planets and the structure of the universe. In practical terms, they do their jobs extraordinarily well, and yet the desire to unify them persists. Part of that desire comes from a long-standing expectation in science that nature should be describable in a coherent way. Not necessarily simple, but internally consistent. The idea that the universe would require two fundamentally incompatible descriptions feels unsettling, even if both descriptions work where they are applied. But is that discomfort scientific or philosophical? And throughout the history of science, there have been moments when different descriptions coexisted without immediate unification. Heat was understood long before its connection to microscopic motion was clarified. Electricity and magnetism were once separate phenomena. Light was described successfully as a wave even when its deeper nature remained mysterious. In each case, unification eventually arrived, and with it came deeper understanding. These successes encouraged the intuition that unification is not only desirable, but inevitable. That if gravity and quantum physics do not yet align, it is only a matter of time and ingenuity. Still, it is worth asking whether that expectation always needs to be fulfilled. Nature does not promise simplicity. it does not promise that every successful description must emerge from a single framework. Sometimes different levels of description coexist because they address different questions. A weather forecast does not require a molecular description of air. A map does not need to show every grain of sand to be useful. In this light, the coexistence of gravity and quantum physics could be seen not as a failure, but as a reflection of scale. Each theory explains what it is meant to explain. Each leaves certain questions untouched because those questions belong to a different level of description. This raises a subtle question. When physicists ask for a theory of quantum gravity, are they seeking better predictions or a more satisfying story about reality? In many cases, the predictions already work. The lack of unification does not prevent technology from functioning or observations from being made. Satellites remain in orbit. Atoms behave as expected. The universe expands in a way that can be measured and modelled. What feels missing is not predictive power, but conceptual unity. That sense of missing unity can be deeply motivating. It drives inquiry forward and pushes understanding into new territory. But it can also blur the line between scientific necessity and philosophical preference. Wanting the universe to make sense in a particular way does not guarantee that it will. This does not mean the search for unification is misguided. It means it is worth being honest about its motivations. Some questions are asked because they lead to better predictions. Others are asked because they lead to deeper coherence. Both are valid, but they are not the same. There is also the matter of explanation as reduction. Often to explain something means to show how it arises from simpler pieces. Atoms explain chemistry. Chemistry explains biology. Biology explains aspects of behaviour. This layered approach has been enormously successful, but not everything yields easily to reduction. Some patterns emerge only at higher levels. Temperature is not found in individual molecules. Pressure is not a property of a single particle. These concepts are real and useful, but they are not fundamental in the same way as the entities beneath them. Gravity could occupy a similar position. It might be fundamental, or it might be emergent. It might be something that demands quantization, or something that arises naturally when many quantum systems interact in a particular way. In either case, explanation may not mean reducing gravity to smaller pieces, but understanding how it fits into a broader hierarchy of description. This possibility complicates the idea of explanation further. If gravity emerges from deeper structures, then explaining gravity would not mean writing down a single equation that governs it at all scales. It would mean understanding how different descriptions connect, overlap, and give rise to one another. Such explanations tend to feel less final. They trade neat closure for layered insight. There is also a human element to explanation that is easy to overlook. Explanations are not only about nature, they are about how minds make sense of what is observed. A good explanation feels satisfying. It reduces surprise. It creates a sense of understanding even when complexity remains. This psychological aspect matters because it shapes which questions feel urgent and which feel acceptable to leave open. The discomfort around gravity and quantum physics may arise not from any practical failure, but from a sense that the story of the universe is unfinished in a way that feels personally unsatisfying. That feeling can be productive, but it can also lead to impatience. It can tempt one to demand answers before the evidence is ready to support them. A slower approach accepts that explanation sometimes unfolds gradually, that different layers of description can coexist for long periods, that understanding can deepen without necessarily converging into a single unified picture right away. This chapter invites that slower view. Rather than asking whether gravity must be unified with quantum physics, it asks what would count as success if it were. Would success mean a single framework from which both theories emerge naturally? Would it mean new predictions that can be tested? Or would it mean a conceptual shift that changes how space, time, and matter are thought about entirely? It is possible that the final explanation will look very different from what is currently imagined. It may not resemble a simple extension of existing theories. It may require letting go of assumptions that feel deeply ingrained. Or it may turn out that explanation, in this case, does not mean unification at all. It may mean learning to live comfortably with multiple descriptions, each valid within its domain, connected by careful translation rather than complete reduction. This is not a retreat from science. It is an expansion of what science is allowed to be. Physics has always balanced ambition with humility. It seeks patterns, but it also respects limits. It builds models, but it revises them when necessary. It explains, but it also learns when explanation must remain provisional. The question of gravity in quantum physics sits squarely in this balance. It challenges not only equations but expectations. It asks whether understanding requires closure, or whether some openness is an essential part of knowing. There is no need to answer that question here. In fact, answering it too quickly would miss the point. Instead, this moment offers a chance to linger, to consider what explanation really provides, to notice the difference between knowing how something behaves and knowing why it behaves that way, to recognize that science can be powerful even when some questions remain unresolved. In the quiet space between prediction and understanding, curiosity continues to do its work, not rushing toward a conclusion, but deepening awareness of what is known, what is assumed, and what remains to be discovered. And sometimes that pause is itself a form of explanation. Not knowing is often framed as a problem to be solved, a gap to be closed as quickly as possible. In everyday life, uncertainty can feel uncomfortable. It suggests inefficiency, delay, or lack of progress. But in science, not knowing carries a different weight. It marks the boundary of what has been carefully explored, and it quietly defines where curiosity is still free to wander. The absence of a theory of quantum gravity does not leave physics in disarray. Most of what can be observed, measured, and built continues to function beautifully without it. Atoms behave as expected. Stars burn steadily. Galaxies evolve over immense spans of time. The universe remains intelligible across an extraordinary range of scales. And yet there are places where understanding softens. Black holes are one such place. Their outer behavior can be described with impressive precision. Orbits, radiation from surrounding matter, and the ripples produced when they collide all fit neatly within existing frameworks. But as attention turns inward, toward their deepest regions, certainty fades. Without a theory that unites gravity and quantum physics, the true nature of what happens there remains partially veiled. This veil is not dramatic. It does not signal danger or collapse. It simply means that some questions cannot yet be answered with confidence. What happens to information that falls into a black hole? How space behaves at the smallest possible scales? Whether time itself has a granular structure? These are questions that sit just beyond current reach. The same is true when thinking about space and time more broadly. Gravity describes space and time as smooth and continuous. Quantum physics suggests that, at some level, nature is built from discrete elements. Without a unifying framework, it remains unclear how these views fit together. Does space have an underlying structure? Does time flow continuously? Or does it progress in subtle steps? Or are these questions themselves based on assumptions that will eventually need revision? These limits do not indicate failure. They indicate depth. Every well-developed scientific theory has boundaries where its language begins to blur. Newton's laws work extraordinarily well until speeds approach that of light. Classical physics explains heat and pressure until individual atoms demand attention. Each time, the edge of understanding did not signal the end of inquiry, but the beginning of something richer. The absence of quantum gravity places current physics at such an edge. It means there are regions of reality where descriptions must remain provisional, where models can gesture toward behavior without fully capturing it, where confidence gives way to careful inference. This can feel like a cost, but it is also an opportunity. Without a complete theory, black holes become more than objects to catalogue. They become questions embodied in matter and geometry. They invite thought experiments, careful observation, and new ways of asking what space and time really are. The lack of final answers keeps the conversation open. There is also a limit on how far cosmology can currently reach. Models of the universe's earliest moments grow increasingly tentative as they approach conditions where gravity and quantum effects must have interacted strongly. The story remains compelling, but the opening pages are written in pencil rather than ink. This does not diminish the story, it adds texture. It reminds us that the universe is not obliged to reveal itself all at once. That understanding arrives in layers, often with long pauses between them. The cost of not knowing is not ignorance, but patience. Importantly, nothing essential is broken by this uncertainty. Life does not depend on a theory of quantum gravity. Technology does not stall. Navigation systems do not drift off course. The unanswered questions sit at the edges of experience, not at its centre. This allows curiosity to remain gentle rather than urgent. There is no looming deadline imposed by nature. The universe has waited billions of years already. It will continue to wait while understanding catches up. This removes pressure and replaces it with space for careful thought. Ignorance, in this context, is not an empty void. It is a region filled with possibility, a space where new ideas can form, where assumptions can be tested, and where unexpected connections can emerge. It is where imagination and discipline meet. Historically, such spaces have been fertile. They encourage humility because they resist quick answers. They encourage creativity because familiar tools no longer suffice. They encourage collaboration because no single perspective is enough. Even the language used to describe what is unknown matters. Framing the absence of quantum gravity as a deficiency suggests something is missing that ought to be present by now. Framing it as an open question acknowledges that understanding unfolds on its own schedule. This perspective changes how the cost of not knowing is felt. Instead of loss, there is invitation. Instead of anxiety, there is room. There is also a quiet honesty in admitting limits. It reminds science of its human scale. Knowledge grows through effort, error, revision, and time. Some questions take generations to mature, some may never be fully resolved. This does not diminish their value, it often enhances it. Black holes, the structure of space, the nature of time, these are not practical inconveniences waiting to be fixed. They are deep features of reality that reward slow attention. The lack of complete understanding keeps them alive as subjects of wonder rather than closing them off as solved problems. In this sense, not knowing has a cost only if certainty is demanded. If certainty is relaxed, what remains is curiosity, patience, and openness. There is also a subtle benefit. When answers are incomplete, imagination is disciplined rather than constrained. Ideas must remain tentative. Speculation must stay gentle. This encourages careful thinking rather than dramatic claims. It keeps inquiry grounded. The absence of a theory of quantum gravity does not leave a hole in knowledge. It leaves a horizon, a boundary where current understanding fades gradually rather than ending abruptly. Beyond it lies not chaos, but silence. A silence that invites listening. That silence has shaped science before. It shaped the search for the nature of a light. It shaped the understanding of atoms. It shaped the recognition that space and time are not fixed. Each time, The unknown was not an obstacle to be removed, but a guide pointing toward deeper insight. For now, the cost of not knowing is simply that some questions remain unanswered. In return, there is the gift of wonder, the freedom to ask without rushing to conclude, the reminder that the universe is larger, subtler, and more patient than any single framework can capture at once. In that space of not knowing, curiosity continues to breathe. Foundational questions tend to linger quietly in the background of science, sometimes for decades, sometimes for centuries. They do not interrupt daily progress or prevent useful work from being done. Experiments continue, technologies improve, observations accumulate, and yet beneath that steady motion, unresolved questions exert a subtle influence, shaping where attention drifts and which ideas feel worth pursuing. The problem of gravity in quantum physics belongs to this category. It does not interfere with ordinary calculations or practical applications. Most of the time, it can be set aside without consequence. But its presence changes how physicists think about the limits of current understanding and the possibilities that lie beyond them. History suggests that such gaps are rarely sterile. When a theory works well but leaves something unexplained, it often signals that a deeper layer is waiting to be uncovered. Not immediately, and not on command, but eventually. The gap becomes a kind of intellectual pressure, gently guiding curiosity toward new directions. There are many examples of this pattern. Before the structure of atoms was understood, chemistry still functioned remarkably well. Reactions could be predicted, substances could be combined and transformed, but the unanswered question of what matter was made of continued to hover in the background. When that question finally found a clearer answer, it reshaped not only chemistry, but physics, materials science, and technology in ways that could not have been fully anticipated. Similarly, the behavior of light puzzled scientists for a long time. It could be described as a wave with great success, yet certain observations resisted that picture. Those resistances did not halt progress. They waited. And when a deeper understanding emerged, it did more than solve a specific problem. It opened entire fields and changed how energy, matter, and information were understood. These breakthroughs did not arrive because someone rushed them into existence. They arrived because questions were allowed to remain open long enough for the right ideas and tools to develop. Patience was not a delay. It was part of the process. The situation with gravity in quantum physics fits this pattern comfortably. The absence of a unifying framework does not suggest stagnation. On the contrary, it has inspired new ways of thinking about space, time, and matter. It has encouraged physicists to examine assumptions that once seemed beyond question. Even without a final answer, the question itself has already influenced the shape of inquiry. This influence is often indirect. Foundational problems encourage the development of mathematical tools, conceptual frameworks, and experimental techniques that find uses far beyond their original motivation. Work done in pursuit of deep understanding often spills outward, enriching other areas in unexpected ways. There is also a reassuring lesson here about timelines. Scientific understanding rarely unfolds on human schedules. Important ideas often take decades to mature and sometimes longer. Theories are proposed, revised, challenged, and refined across generations. This slow pace is not a sign of weakness. It is a reflection of how carefully knowledge is built. In this context, the lack of urgency surrounding quantum gravity is not a problem. It is a feature. The universe does not demand immediate answers, and science does not benefit from forcing them. Progress that lasts tends to be deliberate, layered, and resilient. Trust in slow science means accepting that some questions are meant to be lived with for a while. They shape thinking even when they remain unanswered. They encourage humility and persistence rather than haste. They remind researchers that understanding is not a race, but a conversation carried forward over time. There is also comfort in recognizing how much has already been learned without resolving every foundational issue. Physics today explains an astonishing range of phenomena with clarity and precision. From the behavior of subatomic particles to the evolution of galaxies, the picture is rich and coherent across most scales. The unresolved questions stand out precisely because so much else works so well. This perspective helps keep the problem in proportion. The inability to unify gravity and quantum physics does not cast doubt on the rest of science. It highlights the depth of the universe, not the fragility of understanding. Foundational gaps matter because they keep science honest. They prevent complacency. They ensure that even the most successful theories remain open to refinement. Without such gaps, progress might slow, not because everything is understood, but because curiosity has nowhere obvious to go. There is a gentle irony in this. The things that are not yet understood often provide the strongest motivation for discovery. They act as signposts rather than roadblocks. They point toward areas where familiar language may no longer suffice, inviting new ways of thinking to emerge. This has been true before, and there is no reason to expect it to be different now. Whatever eventually resolves the tension between gravity and quantum physics will likely do more than close a conceptual gap. It will reshape understanding in ways that are difficult to predict from the present vantage point. That uncertainty is not unsettling, it is reassuring. It suggests that the universe still has room to surprise, and that science remains a living, evolving endeavour rather than a finished catalogue of facts. In the meantime, progress continues on many fronts. Observations grow sharper, experiments grow subtler, ideas cross-pollinate between fields. The foundational problem remains, not as an obstacle, but as a quiet companion to this broader journey. Trusting slow science means trusting that insight accumulates even when conclusions are postponed. It means valuing careful thought over dramatic claims. It means recognizing that some of the most important advances arrive not through sudden revelation, but through long periods of preparation. The question of gravity and quantum physics still matters, because it keeps that preparation alive. It reminds science that understanding has depth as well as breadth. It encourages patience in a world often eager for immediate answers, and perhaps most importantly, it reinforces a simple truth. The universe does not reveal itself all at once. It invites exploration at a pace that rewards attentiveness rather than urgency. Foundational questions persist not because they are failures, but because they are fertile ground. In that sense, the continued presence of this problem is not a sign of something missing. It is a sign that discovery is still unfolding, quietly, steadily, and with no particular hurry at all. Science is often imagined as a steady march towards certainty, a sequence of questions answered, mysteries resolved, gaps neatly closed. From a distance, that story can seem reassuring. It suggests a destination where understanding is complete and the universe finally makes sense in a finished, polished way. But lived science rarely feels like that. Most of the time, science moves forward while carrying uncertainty alongside it. Explanations work well enough to be trusted, yet leave edges unexplored. Models predict outcomes accurately, yet rest on assumptions that are known to be incomplete. Progress does not wait for perfection. It proceeds with what is available, refining understanding step by step. This is not a weakness of the scientific process. It is one of its strengths. Living with an incomplete picture requires a particular kind of humility. It means accepting that knowledge can be reliable without being final, that explanations can be useful without being ultimate, that understanding can deepen without ever fully closing the circle. Gravity and quantum physics offer a clear example of this posture. Both theories are trusted, both are tested, both are used every day to make predictions that work, and yet they do not fit together cleanly. Rather than forcing a premature resolution, science has learned to work carefully within this tension. This way of working can feel unfamiliar outside science. In many areas of life, uncertainty is treated as something to eliminate quickly. Decisions are expected, answers are preferred, ambiguity can feel uncomfortable. Science, by contrast, has learned to tolerate ambiguity for long periods, sometimes for generations. That tolerance creates space. It allows ideas to mature slowly. It allows evidence to accumulate before conclusions are drawn. It allows mistaken paths to be explored without panic, because retreat and revision are part of the process rather than signs of failure. There is also a quiet confidence in this approach. Scientists trust that the universe is consistent, even when it is not yet fully understood. They trust that unanswered questions are not signs of chaos, but indicators of depth. This trust makes it possible to remain curious rather than anxious in the face of uncertainty. Certainty and curiosity behave very differently. Certainty closes conversations. Once something is declared finished, attention moves elsewhere. Curiosity, on the other hand, keeps questions alive. It invites revisiting ideas, re-examining assumptions, and listening more carefully to what nature is showing. In physics, certainty has often been provisional. Concepts once thought final have later been absorbed into broader frameworks. What mattered was not that earlier ideas were wrong, but that they were incomplete. Each stage of understanding provided a stable platform from which to see further. This layered structure of knowledge is comforting when viewed slowly. It suggests that understanding does not collapse when gaps appear. It expands. Living with an incomplete picture also encourages modesty. It reminds science that no single perspective captures everything. Different descriptions can coexist, each illuminating a different aspect of reality. The absence of a single, unified story does not imply confusion. It reflects the richness of the subject. There's a gentle balance here. Science does not celebrate ignorance, but it does respect it. It distinguishes between not knowing because something has not been studied, and not knowing because the question itself reaches beyond current tools. The latter is not a deficiency, it is a frontier. Frontiers are not meant to be crossed immediately. They are meant to be approached carefully. This attitude helps explain why the lack of a theory of quantum gravity does not generate alarm. There is no sense that something urgent has been missed. Instead, there is recognition that some questions unfold slowly, revealing their structure only after long periods of preparation. That preparation includes developing new mathematics, new experimental techniques, and new ways of thinking. It also includes learning how to sit comfortably with uncertainty, without letting it harden into dogma or dissolve into speculation. Emotionally, this stance can be settling. It removes pressure to resolve everything at once. It replaces urgency with patience. It allows appreciation of how much is already understood, even as attention remains open to what is not. There is even a quiet joy in this incompleteness. It keeps discovery alive. It ensures that wonder does not end with explanation. Each answer opens further questions, not as a burden, but as an invitation. In the case of gravity and quantum physics, living with an incomplete picture means accepting that the universe may not yet be ready to give up all its secrets. Or perhaps that understanding has not yet learned how to ask the right questions in the right way. Either possibility is acceptable. Science does not require certainty to function. It requires honesty, curiosity, and care. It advances not by pretending to know more than it does, but by clearly marking where knowledge ends and inquiry begins. This clarity builds trust. When science admits its limits, it demonstrates confidence rather than weakness. It shows that understanding is grounded, not inflated, that claims are proportional to evidence. As the journey through gravity and quantum physics nears its later stages, there is no need for dramatic resolution. The absence of final answers does not leave a void. It leaves a landscape still open to exploration. That openness can feel peaceful when viewed in the right light. It suggests that understanding is not something to be completed, but something to participate in, a process rather than a product. Living with an incomplete picture does not mean living with confusion. It means living with awareness, awareness of what is known, awareness of what is uncertain, awareness of how much patience the universe seems to require. In that awareness, curiosity becomes steady rather than restless. Questions remain alive without demanding immediate closure. Reflection becomes possible without disappointment. The universe does not insist on being fully understood all at once. It allows understanding to arrive gradually, layer by layer, with long pauses in between. And science, at its best, learns to move at that pace. Gravity has often been framed as a problem, a stubborn holdout, a theory that refuses to fit neatly into the elegant structures built by modern physics. When viewed this way, its resistance can feel like an irritation, a loose thread left dangling after so much careful work. But there is another way to see it. Gravity can also be understood as an invitation, not an obstacle to be removed, but an opening. A place where the universe has chosen not to be fully transparent, offering instead a quiet reminder that understanding is still unfolding. Seen from this angle, gravity's refusal to cooperate completely is not a failure of science, it is a feature of reality. The universe does not present itself as a finished puzzle with all the pieces laid out in advance. It reveals patterns slowly, sometimes generously, sometimes reluctantly. Gravity, in all its familiarity, still carries an element of reserve. It guides motion, shapes galaxies, anchors planets, and keeps feet on the ground, all while holding back something essential about its deepest nature. That restraint is not hostile, it is patient. Mystery has always played a role in science, not as a flaw to be erased, but as a condition that keeps inquiry alive. Every major advance has emerged not from complete certainty, but from moments when existing explanations reach their limits and quietly ask for more. Gravity occupies one of those moments now. It does not behave incorrectly. It behaves beautifully. It simply behaves in a way that suggests there is more to learn. Its smoothness, its universality, its intimacy with space and time all hint at deeper structure without spelling it out. It invites attention without demanding resolution. Unanswered questions serve an important function here. They prevent science from becoming static. They keep curiosity from hardening into dogma. They ensure that even the most successful ideas remain open to revision, refinement, and surprise. This openness is not weakness, it is vitality. When gravity is treated as an invitation rather than a failure, the emotional tone of the problem changes. There is less pressure to fix something immediately and more room to listen, less urgency to force an answer, and more willingness to let understanding mature. This attitude aligns with how science has always progressed at its best, slowly, carefully, with long stretches of patience punctuated by moments of insight that only arrive after enough groundwork has been laid. Gravity's mystery encourages this pace. It also reminds us that the universe does not owe us clarity on our preferred timeline. Knowledge arrives when questions are asked in the right way, with the right tools, and sometimes that alignment takes longer than expected. The waiting is not wasted time. It is part of the process. There is something quietly comforting in this. It suggests that not everything needs to be resolved in order for understanding to be meaningful. that participation in inquiry matters as much as conclusion. That wonder does not disappear when explanations improve, but often deepens. Gravity, after all, is not an abstract puzzle floating somewhere beyond experience. It is woven into everyday life. It is felt without being seen, trusted without being fully understood. Its mystery does not prevent it from being useful or reliable. Instead, it adds depth to something already familiar. In this way, gravity mirrors many aspects of reality. There are things that work, endure, and support life without revealing every detail of their inner workings. Understanding grows around them gradually, never quite exhausting what they have to offer. Science thrives in this space between knowledge and mystery. It advances by respecting what is known while remaining attentive to what is not. Unanswered questions are not signs of failure. They are signs that curiosity still has room to move. As this journey through gravity and quantum physics settles into its final stretch, there is no need to force closure. The story does not demand a final equation or a definitive framework to be complete. It has already revealed something important about how understanding unfolds. Gravity, in resisting easy explanation, keeps science awake. It encourages humility. It rewards patience. It reminds those who study it that reality is richer than any single description. That richness is not something to overcome, it is something to inhabit. Allowing curiosity to soften into rest does not mean abandoning inquiry. It means trusting that understanding continues even when it pauses, that questions can remain open without becoming unsettling, that mystery can coexist with clarity. Gravity remains steady, familiar, still inviting thought. And perhaps that invitation is not asking to be answered immediately, but to be held gently, to be returned to again and again as understanding slowly finds new ways to grow. In that quiet openness, science continues its work, not rushing, not demanding, simply listening and waiting and wondering. Gravity has carried this entire journey quietly in the background. It has shaped planets and galaxies, curved space and slowed time, and yet remained familiar enough to fade from daily notice. From the beginning, the question was never whether gravity works. It clearly does. The question was why something so reliable, so steady, still resists being fully woven into the deepest descriptions of reality. That question remains open, and that is not a failure. Physics has already come remarkably far. It has learned how atoms hold together, how light behaves, how stars are born and die, how galaxies assemble, and how the universe expands across immense stretches of time. It has uncovered patterns that allow predictions of astonishing precision, turning curiosity into understanding again and again. Along the way, it has also learned something quieter, that not every question yields immediately, that some mysteries persist not because they are neglected, but because they are deep. Gravity sits among these, familiar enough to trust, subtle enough to resist final explanation. There is beauty in that balance. Not knowing everything does not diminish what is known. It gives it context. It reminds us that understanding grows outward from what is solid, not inward from what is missing. The unanswered questions do not erase the answers already earned. They rest beside them, expanding the landscape rather than breaking it. Gravity remains part of everyday life throughout all of this. It is present in the weight of a cup resting on a table, in the slow arc of a thrown stone, in the quiet pull that keeps feet grounded and oceans held close to the planet. It does not demand attention. It does not announce its mystery. It simply continues. And perhaps that is fitting. The universe does not seem built for complete disclosure all at once. It reveals itself gradually, allowing understanding to deepen while leaving space for wonder. Gravity, in its refusal to fully explain itself, becomes a reminder of that pace. A reminder that knowledge is not a finish line, but a process unfolding over time. The question of why quantum physics cannot yet explain gravity remains open, not as a gap to be filled urgently, but as an invitation. An invitation to keep asking, refining, and listening. An invitation to accept that clarity and mystery often coexist. There is calm in that acceptance. Calm in knowing that understanding does not require final answers to be meaningful. Calm in recognizing that curiosity does not have to resolve into certainty to be worthwhile. Gravity will continue to shape the universe whether it is fully understood or not. Physics will continue to explore it with patience and care, and the space between what is known and what remains uncertain will continue to be where discovery quietly lives. For now, it is enough to notice how much has already been learned, how much still invites attention, and how gently the universe seems to allow both to exist at once. Gravity pulls downward, time moves forward, questions remain, and the journey of understanding continues steadily without hurry.